Now we are done with the microscope. So the second optical instrument which we are going to discuss is telescope. So look at here, what is different between telescope and microscope? All right. So very simple difference. All right, in a very fundamental level. Microscope is an optical instrument which is used to see a very small, tiny object which is close to you, and telescope is an optical instrument which is used to see a far object. All right, which is used to see a very far objects like stars, like astronomical objects, and even in case of a terrestrial, used to see a very far object. All right, and again, before I talk about two important parameters for telescope and a microscope, that is resolving power and magnifications. So in case of microscopes, the magnification plays greater role in a microscope than resolving power or resolutions. However, in case of telescopes, it is the resolutions or resolving power of a telescope which plays greater role. All right. So this is what we have. And again, for telescope, broadly speaking, we divide telescope into a two-part or two. That is terrestrial telescope. This is a terrestrial telescope. So terrestrial telescope, the terrestrial, right? Terrestrial is an object that is found on Earth's surface. This object found on Earth's surface is what we call as terrestrials, right? And so telescope, which is used to see on the Earth's surface, is normally what we call as a terrestrial telescope, and the final image is always erect. This final image is always erect, right? For terrestrial telescope, final image is erect, and astronomical telescope is a telescope which is used to see astronomical objects such as stars, planets, moons, and all, right? So this telescope, the final image of such a telescope is inverted. Final image for such a telescope is what we call as inverted. Alright, this is the difference, right? And again, for a terrestrial telescope, it consists of a three lens, convex lens, and for astronomical telescope, it has only two lenses, two converging lenses. Alright, so as far as our syllabus is concerned, we have no, the terrestrial telescope is not there. It is only, we have only astronomical telescope. So we will focus only on astronomical telescope. So again, when we talk about telescope, again we divide the telescope into two parts. One is a reflecting telescope and other one is reflecting telescopes. Reflecting telescope, and second one is reflecting telescopes. This is what we have. So reflecting telescope is a telescope where we use lens, and reflecting telescope is a telescope where we use concave mirror. So mirror, right? The reflecting is taking place in a reflecting telescope, and the refraction is taking place in a reflecting telescope. So this is an example of reflecting telescope. So look at here. Whenever I told you just now, object should be at very far. So we call it as infinity. So this tells that object at infinities. How do you know that object is infinities? The rays are parallel. These rays are parallel to each other. If rays are parallel to each other and incident on a lens, and for that, we conclude that object is at infinity. Again, in case of a reflecting telescope, it consists of two lenses. This is called objective lens. Alright? And second one is called eyepiece. Unlike microscope, for telescope, objective lens, this objective lens should have a large focal length and aperture or a size of objective lens is much bigger. Alright, so this is very, very important. So this lens should have a bigger focal length and larger focal length, and the size should be much bigger. Alright, and this is the eyepiece. Alright, this is the eyepiece. And now again I say that the focal length, again I just say objective lens has a focal length f0. Alright, and then eyepiece lens has a focal length fe. Alright, now what I'm going to do is, if I keep an image at infinity, and we are going to find out angular magnification. Alright, so now look at here again, as we have done in a microscopes. So the image of an object this is the image of an object, alright, which is diminished. Why? Because object is at very far. Alright, and this image of an objective lens, again I am repeating, image of an objective lens act as an object for eyepiece. And now look at here, since this act as an object for eyepiece, we are going to get final image. Again, a final image is inverted. This is a final image which is inverted and which is at infinity, if you are going to put, or if you are going to keep image at far point. So this is the point. Alright, now for microscope also we are going to find out angular magnifications. For microscope, for telescope also we are going to find out angular magnifications. So angular magnification is equal to beta divided by alpha. What is beta and what is alpha, right? So this is angular magnification is defined as a ratio of angle, alright, subtended at I by the final image to angle subtended at the objective lens by the object. So this is what we have. Alright, this alpha is angle subtended at the objective lens by the object, and this is an angle subtended at I by final image. So this is what we have. So now look at here again. I would like to write here. I'm going to extend, since this is a parallel, I would like to keep something like this. So this is parallel, all are parallel, so therefore I'm going to keep this. Yeah. I'm going to keep this, say, beta, since this is parallel, all are parallel, why? Because images at infinity, this is beta. So now how to find out? Let's say again 10 beta is how much? 10 beta is equal to h divided by fe. Alright, and then what about tan alpha? Tan alpha is equal to how much? H divided by F naught. Alright, so since beta is small, tan beta is equal to beta, which is equal to H divided by F naught. Tan alpha is equal to alpha, which is equal to S divided by F naught. Alright, now what is magnifications? I just divide this. I substitute this. Finally, I'll get what is beta? H by Fe. What is alpha, which is reciprocal? F naught divided by H. Cancel out. So this angular magnification is F naught divided by Fe. So this is the magnifications. This is the magnifications. So this is the magnifications. Alright. I'll write here by red pen. M is equal to F naught divided by Fe. So if I'm keeping F naught huge and keeping Fe small, obviously magnification is going to increase. Magnification is going to increase. Alright. So therefore, whenever we design a telescope, we always keep objective length as big as possible. Right. So what are the advantages? Alright. Or what are the significance of keeping objective length big, right? If objective length is big, again in case of a telescope, we talk about two important factors, that is light gathering power, and resolving power, resolutions or resolving power. So if I keep objective length big, obviously more light enters into this, and more light from an object it enters through this, we get the brightness of the image would be much higher. And again, maybe in next class, next chapter, we'll discuss resolving power. Resolving power is all determined by the size of an objective lens or aperture of an objective lens. Again this, and again for magnifications, F naught should be big. If F naught is big, magnification is going to increase. We can increase magnification. So therefore, again very important. What are the significance of keeping objective lens big? Very two important factors. One is light gathering power is going to increase, and the resolving power or resolution is going to increase. And then again, so we can't go on and increase the objective length. So we cannot. This is the problem, right? This is the limitation, right? So in case of refracting telescopes, I can't go on and increase objective length. Why? Because we have few limitations are there. So the disadvantages of refracting telescopes. Again, if I design a huge objective lens, then the thickness of a lens is going to become thick. If I design a big, let's say a 1 meter size of refracting telescope objective lens, then the thickness of a lens is going to increase. If a thickness of lens is going to increase, then the lens act like prism. So therefore, this is what we call as a chromatic aberrations. Chromatic means lights. So aberration means there is an the color, right? You see a different colors when you see through a telescope. Why? Because this lens act like prism, right? And another again one limitation is the spherical aberrations, right? So it is much easier to design a small spherical lens than designing a big spherical lens, right? If I design a big spherical lens, the curvature of a lens wouldn't become so smooth, so there may be some irregularities, or there may be some aberrations, all right, all along the surface of a spherical lens. So therefore, this will give you again different images, right? Again, the third one is, it is very expensive, all right. Designs 1 meter size of convex lens is going to be a very expensive, and it is also difficult, right? Difficult and expensive to make a nerd size lens. And again, the last limitation is that maybe I say we have to keep telescope either at top at the buildings, or we are going to send this to a space center, right? So if it is huge, heavy, it is very difficult, right, for mechanical support. So why? Because if I have a 1 meter size of convex lens, it is very, very difficult to hold a telescope all along a rim, right? Why? Because this is what we call as mechanical support. So these are the 4 limitations of a reflecting telescope, right? Having this, now scientists design another telescope, which is what we call as reflecting telescope. Reflecting telescopes. Reflecting telescope. Reflecting telescope. Reflecting telescope. So this is a reflecting telescope, schematic diagram of a reflecting telescope. So this is what we have. Let's say I design this concave. This is a concave, what we call as objective mirror, huge objective. All right. So this the image object at infinity. How do you know that object is at infinity? The rays are coming parallel to each other. All right. And then this is the concave lens. The lens and the ray undergo reflections, and maybe sometimes we keep observe inside a telescope and observe the image, or we keep this secondary mirror, that is a convex mirror, which again is reflect that, and this is the eyepiece, and we could observe this. All right, we could observe the image. So this is how it goes. This comes from an object, far object, astronomical object, and then reflect back, and finally we see through eyepiece. This is what we call as reflecting telescope. This is what we call as reflecting telescope. So advantages of a reflecting telescope is this, right? So since the reflection is taking place, since the reflections are taking place in a reflecting telescope, no chromatic aberrations. There is no chromatic aberration in a mirror. So therefore there is no dispersion taking place. Again, another very important is that if a parabolic reflecting surface is chosen, the spherical aberration is also removed. So if I go and choose a parabolic surface, and somehow we could have to remove all spherical aberrations. And finally, mechanical support. So you are going to design a reflecting surface, which is much easier to design than a lens. So mechanical support is much less problem, since mirror weight much less than a lens. So these are the 3 very important points which help the scientists to design a reflecting telescope. So you can go on and design so big telescopes. Unlike in case of a reflecting telescope, we can't built a refracting telescope of size 2 meter, right? So therefore in India, in our textbook it has written that in India the biggest telescope is found in Tamil Nadu. The size is of 2.34 meter. That's diameter, right? Meter in diameter. And the biggest telescope, largest telescope in world is found in United States of America, that is Hawaii. The size is of 10 meters. Size is of 10 meter in diameter. So this is what we have. So therefore reflecting telescope is much superior than refracting telescope. Why? Because we could able to remove all these difficulties. Alright. So now this is an example, this is a ray diagram. This is not there in your syllabus. Just for your understanding, I have brought you terrestrial telescope. Alright. So unlike astronomical telescope image is always inverted, which I explained you. And now for astronomical telescopes, it is always erect. It is always erect. So it consists of 3 lens, and this is what we call as an erecting lens. This lens provides the final image erect, right? So this is astronomical terrestrial telescope. So this is how we differentiate between astronomical telescope and terrestrial telescope. Alright, so with this we come to an end of this chapter, ray optics. So I hope you have gained some understanding, or so maybe if you have any doubt, or maybe I was not able to do much problem solving part. If maybe next session I'll do a problem part, maybe 2 or 3 problem part I'll do it, right? So with this we have done with chapter 4, ray optics. Thank you.